Hi folks. We're looking at one last example in kinematics in one dimension. So right here we have a position function in purple. And we want to see what we can tell about velocity and acceleration from it. I mean, I guess you could tell a story here that you started a little bit east from home, you went further away, you stopped, you came back and you ran right past your home, and then you came back towards your home and stayed there at the end. That's one thing we could say. But let's think about that purple graph as being position, and S prime would give us velocity. Okay? And S prime means slope of S, I guess. Okay? So what can we say about the slope of S all the way through here? Let's start right at the beginning. The slope of S is positive, or the function's increasing right up to here. Okay, so we could say velocity is positive for the first little while. And then velocity is 0 because the position is staying exactly the same right here. So it's not changing at all. Velocity is 0. But I guess more simply, slope is 0. And then, maybe that's a little too far, and then slope becomes negative. And that means velocity is negative because your distance from home is decreasing. Okay? Or your position from home is decreasing. And then we go and hit a velocity of 0, just momentarily velocity of 0. And then slope becomes positive again. And then abruptly, we just stop at home. And velocity is 0 as you flop down on the couch at home. Okay? That's essentially what's happening with velocity. Now, acceleration is maybe a little trickier. So S double prime is equal to V prime is equal to A of t. Acceleration, in other words, is the concavity of S. So let's read this. That function starts concave up, but it only lasts so long. So concave up, that means acceleration is positive. Okay? Concave up on the original. And then it becomes concave down for a little bit. So negative. And then it becomes concave nothing. When it's linear, concavity is 0. And then it's concave down, so acceleration is negative. That changes, though, before the slope changes. So it's concave down for a little bit, but around like here-ish, it changes to concave up. Okay, so CD to CU on the original. And it stays concave up probably till about here, I would say. And that is going to be the end of its concave up period. Then it is linear again. Okay? And it stays linear the whole time, though there is this abrupt change right here. But there's no concavity. So that's a reading on what's happening to this graph. Now, if we wanted to go piece by piece and say what's happening, I think it's easier just to read it off the graph. But we could say right here, when they're both positive, you're speeding up. Speed up, okay? And then slow down, where one is positive, one's negative. They're both 0, or more importantly, velocity is 0, so we're stationary. And then you start traveling, decreasing your distance or your position from home. So this is going to be speed up. And then we end up with this little bit where we slow down for a little while. Slow down. And then very briefly turn around and speed up. Speed up. And then this is going to be constant velocity, and the last little bit is going to be stationary. The big ideas here, though, is that if you have a position graph, the slope of the position graph gives you velocity, the concavity of the position graph gives you acceleration. And the relationship between velocity and acceleration are what tell you whether you're speeding up or slowing down. Again, you could take a look at page 267 to 268, numbers 1, and this is most like number 6. I hope this has been helpful. Good luck with the material, folks, and take care.